Hello and welcome to another Focus Finder. And today, first slide is Racecourse over in Horton-le-Spring. 25 passive houses. In 2011 it was the largest passive house scheme to have been constructed early in 2011, and it was first conceived in around about 2008, I think it was. Yeah, it took a few years to get it onto the ground because of global recessions and the like, but no, it's been very successful. So basically, what's the history to Passive House and the quality assurance standards that are linked with it? Well, first of all, the first Passive House was constructed in Darmstadt in Germany in 1991 after a 2-year research exercise undertaken by Professor Bo Adamson and Dr. Wolfgang Feist. And there was a number of years worth of serious study that went on into designing the building. So the initial aspiration was to make it a zero energy building, but as the research continued they determined that it wasn't going to be feasible to achieve that over the whole course of time, and therefore they ratcheted things back and determined that it was going to be practical to set a different kind of threshold. And that means that we've got an energy standard which is 15 kilowatt hours per metre square per annum. So if you get your energy bills out, you'll see it's in kilowatt hours. So for every square metre, it's using 15 kilowatt hours to heat the home, which is the same as saying, should we say, around about 1.5 litres of oil per metre square per annum to heat your home, which is about 90% reduction compared to most average dwellings. So even though it wasn't designed to be zero in terms of zero heating, it was made possible with the introduction of some super insulated shutters that you can see highlighted here. But as I say, it's not really a long-term kind of a viable option. So yeah. The project's now 23 years old at this date in 2014, and yeah, it's still working very well, and the occupants are still happy in there. There's been very little in terms of the need for change. I think only one fan has needed replacing in those 23 years. So for the MVHR system, the mechanical ventilation with heat recovery. So all in all, extremely successful, very comfortable, and very low energy use. So one of the things to think about with a passive house is the fact that the energy flows that are required are actually kind of very much what you could describe as a human scale. If we've got a situation whereby one tea candle every 3 square meters would be enough to heat your home on the coldest day of the year, or an incandescent bulb if you manage to unpack one of those from your storage. Then what you'll find is that'll heat 10 square metres of a home. A person, if you invited a friend round, they'd heat 10 square metres of your home. Toasters, toasters around about 2,000 watts. So that could heat the whole house. And so we're talking about some, as I say, human scale energy flows. The design standard for passive house is to have the heating at only 10 watts per metre square per annum, and that means that we can use the fresh air to heat the property. At least that's the theory. You can, whether you actually choose to do that, there's a range of reasons why you might discuss whether you want to do it or not. But you can use a range of different heat sources, whether it's wood, gas, heat pumps, compact service units, etc., etc. A whole host of technologies can be used. It's really a case of looking at the site and the context to make sure what you're using select is appropriate. And generally what I experience is that using gas or propane tends to be most useful and appropriate, even in remote rural locations. So the principle of a passive house is very simple. It works a lot like a thermos flask, whereby if you put hot drink in it, it'll keep the drink hot, and in the winter, if you put a cold drink in it, it'll keep it cool. So therefore, in the summer you can keep the building cool because it's keeping a lot of the heat out, and you keep the building cool by using night ventilation strategies and things. And then in the winter, you just keep the building locked up. You minimise the opening of windows. You can open the windows if you want to, of course, but in terms of trying to reduce the amount of energy used, you keep the windows shut and batten down the hatches as you'd normally expect in a house, and you massively reduce the amount of energy that you use. So the term passive house refers to a specific construction standard with good standards of comfort in both the summer and the winter, and it has no reliance upon a traditional heating system. As I say, at least that's the theory. So what that means is that we're able to then reduce or remove the radiators, the pipes, the pumps, and the labour that's associated with those services, and we can redirect it into the building envelope so that we can buy better windows, more insulation and the likes. And what that means is that we can effectively throw away the radiator in a metaphorical sense and start to focus on other areas of the construction instead. So that you'll find that there are passive houses with only 1 or 2 radiators in the whole house, and these could be kind of 70 to 100 square metres or more. So the passive house standard itself, now often it gets talked about as being an energy standard, and well, it is in part, but in the manner of speaking, nothing could be further from the truth, because what you actually find is that it's not all about heat energy. It's also very much about comfort, because of course that's why we use energy. What we actually want is to achieve a standard of comfort, and therefore we heat our buildings. So what we've got is a situation whereby we assume in passive house design that people are heating their home to a 20 degrees Celsius. Now this is an assumption, it's not reality. You may live at lower temperatures or higher temperatures. The studies that have been done have demonstrated that people tend to live in passive houses around about 22 degrees Celsius, and that's because people can afford to pay the kind of fuel bills that they're now faced with, and therefore they can afford to be as comfortable as they choose. Those people that want to wear extra jumpers and live at lower temperatures because they might have environmental concerns, of course, they can do that as well. There's not a particular issue to that. We've then got air tightness. Now this is, don't be concerned, this is the building industry's way of describing draft proofing. So what we have here is a very heavily draft proofed building, which is around about 16 times more airtight, more draft proofed than UK building regulations. And what that means is that we don't get the cold drafts across our feet that mean that we would then start to feel discomfort. Because when we feel that kind of discomfort, the consequence of that is that we go and reach for the thermostat and turn the thermostat up by a degree or two, and that of course increases your fuel bills by 10 or 20%. And also, by having a good airtight building, it means you don't get stratified, kind of poorly stratified air. Therefore you've got, that experience where you've got cold feet and a warm head. Well, that's stratified air. Because it's cold air at the bottom and warm air at the top, and when that's more than 2 Celsius difference between your ankles and your head, that's when you experience this kind of uncomfortable feeling. So by designing a building to be airtight, we address that. We've got the windows as well, making sure that they're designed to avoid cold downdrafts and also avoiding issues in terms of radiant discomfort. So therefore you maintain a really high standard of comfort during the coldest day of the year, and that's used to inform the design of the glazing systems and the likes. We also limit our overheating risks to less than 10% during the course of the year, so therefore we're minimal, and where overheating is described as temperatures going above 25 degrees Celsius. Now the 10% is the maximum threshold. If you achieve a target of less than 5%, this is generally considered to be good practice, and in the UK context, certainly for domestic scenarios, this shouldn't really be a problem. We've then got air quality. Well, what we've got to do is we're going to make sure that the building is ventilated appropriately, so this is again, and we're also looking to try and avoid drafts again, so therefore making sure that we've got the ventilation, fresh air supplied to around about 0.3 to 0.4 air changes per hour. Means that we get good fresh air, and this is all backed up by scientific kind of studies that show that your indoor carbon dioxide levels, indoor emissions from your materials, volatile organic compounds, VOCs, these are all controlled, and your indoor humidity is also at an appropriate level really for the majority of the year. And then there's acoustics. Now, and this is again something that's often overlooked with a lot of regulations. Building regulations, for instance, have a much higher acoustic threshold, and that can lead to a large number of people feeling discomfort, acoustic discomfort in their rooms. So, Passive House covers a whole host of different criteria there. Now, I think, well, I've mentioned this on another focus finder, but what we've got here is we've got a graph that's showing building regulations buildings, low energy buildings, passive house buildings, and autonomous off the grid, kind of zero carbon type buildings. And what you see is that you've got the very low embodied energy in blue for the building regulations buildings, low energy buildings, passive house buildings, and then it increases for the autonomous off the grid building. And that's because you've got basically a power station strapped to your roof. You've got all the PV, photovoltaics, you've got the solar thermal panels and that kind of thing, and that increases the embodied energy. So that means not also that you've got more maintenance energy, which is this kind of the reddish tone. Basically, you've got more maintenance to do because you've got to replace all of these pieces of kit. So therefore, you've got to be mindful of that. The energy in use, you can see that with the building regulations building, the yellow, the energy in use is that much greater than any other factor that we've considered. So really making sure that you get that energy in use as low as possible is really the kind of core criteria in terms of thinking about environmental impact considerations and the likes, and also whether it's carbon emissions or whether it's preserving fossil fuels. These kind of things start to become key, and ultimately this ties into the idea of buffering yourself from fuel price rises over time. So really what we're saying here is that the optimum is somewhere around passive house in many respects. And the key thing is that this is recognising the quality assurance methods associated with passive house, not just a numerical target. But there's some verification that the study of 228 homes basically what we see that is on average the homes are performing as we'd expect. Now the mean value in blue is really demonstrating the actual measured values across the first 12 months, but there's a drying out process that takes place whereby you can expect an extra 1.5 kilowatt hours per metre square per annum to be used to dry out the moisture, dry the moisture out from the building fabric in that first year. So therefore, when you adjust for that, then it comes down to around about that 15 kilowatt hours per metre square per annum that we'd be expecting to see. So we can be fairly confident that passive house buildings overall perform as you'd expect, though obviously this is 228 different homes. Each individual home, some has higher consumption, others have lower consumption, so don't necessarily expect your own home to marry up with this perfectly, and you'll be somewhere along this kind of line in many respects, and but on average the buildings perform as we'd generally expect. So what this means is that we can get multiple benefits from single expenditures, and we can harmonise the design in such a way that we are minimising the amount of fuel poverty, we are able to address fuel security, we are able to reduce the impact of peak oil, whilst also reducing the amount of emissions into the atmosphere. And it also goes as far as helping to work with regional trades as well, because you're upskilling regional trades, equipping them with new knowledge and understanding, and this helps to boost the regional economy. Specifically, more particularly the case with retrofit projects. So there are multiple benefits that can arise from the expenditures associated with constructing a passive house, not least improving the comfort of the home, so that you're as comfortable as you can be, and really quite content actually. So the other thing is that there's improved building physics, so we don't get cold, kind of damping corners, we don't get mold growth and things. Now there are 6 basic rules to a passive house. There is having, in an idealised sense, you're going to have a compact building form. Now the smaller the building, the more compact the shape is going to be. Not as and this is purely an argument in terms of thinking rationally about your budget. You could, if you have a more lossy shaped building, so if it's, I always use the analogy, if it was a star-shaped building, and then it's got a lot more surface area for the same amount of floor area, and therefore it loses more heat. And what you find is that you've got to double the amount of insulation in a wall in order to help get the building back down to the performance requirements that we might be chasing. And this is a bit crazy, really. So you want to have a compact building form, as compact as realistic within the context of the brief, so that way you can spend the money most wisely. Air tightness detailing. Now, don't take this as a good example here. This is deliberately here as a bad example. This is what you might typically expect to see on building sites, and it's pretty particularly shoddy work, but at least there is some idea of an air barrier going in. So we've got to get the air tightness right, and working with one building contractor that I know up here in the northeast, Joe Dixon, his first passive house that he ever constructed, he'd never done pressure test on a building before. He got 0.35 air changes per hour at 50 pascals, which was 32 times better than UK building regulations. Phenomenal stuff. So with the right detailing from the design side, and then with the right kind of standard of workmanship, you can get some phenomenal results. Now, getting the insulation right, as I say, this is tied back into the having a compact building form, but we've also got to think about thermal bridging. Now, what a thermal bridge is those little locations around windows and doors where we've put, where we've got alignment issues with insulation, or where we've got structural loads that have been transferred into the ground, and that slices through the insulation, perhaps. And these things have got to be designed out where as much as possible, because they can make a significant impact upon the performance of a building. Now, there's often a discussion about windows and orientation for passive houses. Strictly speaking, passive houses don't have to be facing south. It's beneficial for them to do so, because again this can help reduce the amount of insulation that's required, but it's not an absolute necessity. And you can, as you can see here, you can open your windows in a passive house to help maintain comfort in the summer months. But getting ventilation strategies in place, whether it's the windows or a ventilation heat recovery system, you've got to make sure that it's all been done properly and it's commissioned. So that means that it's been serviced properly as it's been getting installed, to make sure that it works correctly. And then we've got internal gains, which are ways of getting, we get heat from people, from washing machines, from toasters, from showering, all these bits of heat. These are internal gains, and there's considerations that have to be given to that during the design process, when you're not necessarily purely for the certification process, but just in terms of helping to develop a project by project understanding of overheating risks. And also, of course, to try and achieve the 120 kilowatt hours per metre square per annum in terms of the overall primary energy target. That's where internal gains also start to come in a major way. Now, we're not really restricted to any particular building technologies, whether it's external thermal wall insulations. Cavity wall constructions can still be done as well, though I've not represented it here on this particular slide. We've got timber frame, we've got structured insulated panels, we've got all sorts of things, and I thought it'd be interesting to just reflect upon the fact that in Germany 70% of the construction is masonry and only 15% is timber. Meanwhile in Austria, its next door neighbour, 80% of the construction is timber frame. Meanwhile we've got around about 20% which is masonry. So almost a role reversal of the two there, you see. So in the UK, where we've got a very masonry dominated industry, it's not a problem. We can build passive houses using that kind of approach, but you may not. If you want a timber frame passive house, then that can be done. I've done timber frame passive houses, I've done cavity wall passive houses. It all works, and really the key thing is thinking about cost and trying to root down and bed into the local environment, in terms of what the builders know and understand, and how they think they can deliver a project in the most cost effective way. And we can get wrapped up in thinking about the U value. This is the measure of heat loss from a wall or a roof or windows and likes. And these are significantly better than UK building regulations as they currently stand. So, and in the UK climate, actually, we actually tend to be even better than the 0.15 that is generally considered the black stock value for passive houses. And that's because of our wonderful cloudy climate. So we've also got some more esoteric and expensive insulation systems that can be brought into play, but I wouldn't generally advise it. The simplest thing to do is to appreciate and learn to respect the idea of having a thick wall, which I think is a tremendously liberating thing. There's all sorts of things that you can do with a thick wall. You can create bay windows, box windows and things. Have window seats that you might not otherwise have had the chance to do. So here we're looking at some thermal bridging. This is a bit of a crazy graph, and basically what you've got along the bottom is you've got this measure of heat loss from a wall, a U value, and up on the left hand side you have the measure of the thermal bridging, in this case a Y value. I've used UK metrics here because it just helps to explain things a little bit more clearly, because I'm comparing also to UK building regulations. So the blue line is a building with the UK building regulations default amount of thermal bridging, and then the kind of reddish line is the accredited construction details as they stood in 2006 and 2010, and then you've got the green line, you've got the thermal bridging from a project that I worked on. And you can see that basically these lines start to increase on an exponential type curve, an increasing curve as we go, as we track from relatively high U values, 0.7, all the way down to 0.1, which we'd expect at Passivhaus standards. So so by the time we get down towards Passivhaus standards, you can see that you're losing, if you use the building regulations default values, you're losing about 60% of the heat through the fabric through the thermal bridges. Now what this means is that to compensate for these things, you end up putting more insulation into a wall, and you shouldn't have to do that. This is a very simple design decision here. Basically, once you've got the right technical understanding and you understand how to deliver it in the right way, then you can design out these issues and you can actually get all the way down. You can make an 80% reduction in the amount of thermal bridging, and this saves you quite a large amount of money. From memory, I think it saves one client around about £3,500 on insulation. They'd have needed an extra, I think it was 150 millimetres of insulation around the whole house just to compensate for the thermal bridging if we'd have used the default values from building regulations. Air tightness. I've mentioned how that's key. Not only does it help to reduce cold drafts and cold air leaks around your feet, but it also reduces the amount of moisture and condensation damage that can occur to a property. So therefore, if you've got a two-storey home and you've got a 1mm wide gap that is 1 metre long, then you've got, in a two-storey property, you end up with 2 pascals, which is a measure of pressure. You've got so it's very little pressure difference in many respects, but you get moisture transported through that gap over the course of a day, and all in all it totals up to around about 360 grams, and a large proportion of that is going to be condensing into your building fabric. Now as you improve the U values, these kind of risks increase. So as you make the building fabric better, these risks can start to increase. So you've got to make sure that you design the building fabric right. And in Scotland, they've banned cold roofs, as they're known, because of moisture problems. But the core thing is that they haven't really dug down into the reasons why these moisture problems exist, and it's actually because of poor air tightness. When you do the physics, as a couple of people that I'm aware of have, what you find is that once you get down to an air tightness of around about 0.5 metres cubed per metre square at 50 pascals, which is a European standard way of measuring or accounting for the units of air leakage, then what you find is that the timber can cope with those, the amount of moisture that's escaping through the building in those ways. So the risks are that much less. So if you've got a super insulated building, as much as 50% of the heat loss can be through the envelope through poor air tightness. So you want to make sure that you've got a very airtight building, so that you can get the building performing in the most appropriate ways. And I thought it might be interesting to highlight the fact that in Canada, where they build 3 times more airtight than they do in the UK. They build to an air tightness of 3 rather than having a building regulation standard of 10. That's the equivalent of what they've looked at is aggregating, pulling together all of these holes and gaps in the building fabric into one place, and they've looked at how big this area would be, and they've determined that even when you build 3 times more airtight than UK building regulations, it's the same as having about half a door missing from your home. So it's a sort of significant amount of air leakage that's taking place when you're in a regular building. In a passive house, what we're talking about is actually getting that air leakage area down to something akin to a cat flap or a letterbox. Though we don't have letterboxes or generally speaking cat flaps in passive house buildings, there are some smart technical ways to try and introduce them, but generally simple is better. Then we've talked about that, the air tightness in Canada. So one of the key things that you find with passive house is the level of quality assurance that just doesn't really exist in a lot of the construction industry. So not only do we have passive house certified buildings, but windows are also certified, as are the ventilation heat recovery systems. And we also have certified passive house designers, of which I'm one, and we have approved certifiers, and there's a number of those in the UK. Now, at the moment, there's very little in the way of certified passive house constructors. There is now a tradesperson's course or tradesman's course that's getting introduced, but it's still very much a fledgling thing at the moment, and it's not necessarily well bedded in. So at the moment, you need to make sure that the tradespeople get the right kind of training, and that's one of the things that I provide within my scope of services as normal. And this is all part of a risk management strategy as well, because what we don't want is for inexperienced contractors to be overpricing the work that's associated with your project because of their own fear. And what they find is that when they start to look at the construction details, they realise that there's nothing too unfamiliar that's taking place, and it's all within an achievable grasp. So therefore you start to get much more realistic prices in on that basis. Another key quality assurance tool is the Passive House Planning Package, or PHPP. So right from day one I use this as a way of helping to inform my designs. So I'm thinking about the U values that we've talked about, the heat loss through the fabric. We're also thinking about the areas of glazing and using that to try and help us get on track and account for the performance of the building and what might happen. And it's a very accurate tool. This study here looked at 51 or so properties and compared the calculated performance to the measured performance, and on average the PHPP calculations are a little bit adrift, but nothing so substantial, and if anything, in this particular case at least, you're seeing it on the safe side as well. PHPP is a very powerful tool that's been tested and verified using both very highly complex dynamic calculations and also by using reference measurements from existing kind of built properties, built passive houses. So passive house is basically for new build, but you've also got passive house requirements for retrofits. So therefore all of these same energy and performance, comfort kind of criteria exist, though you'll find that the numbers are slightly different. So the air tightness is a little bit more relaxed because it's that much harder to achieve the same high standards of air tightness because you've got a lot of work to do to an existing building. And then we've also got a slightly elevated space heating requirement because again we've got thermal bridges that can be very difficult to address. But many of the other criteria remain the same. The only thing that you'll notice now at the is at the bottom the issues associated with moisture there, and what we're doing is we're designing buildings to minimise the thermal bridging as indeed you would for a normal passive house in truth, to make sure that there's no risk of condensation at kind of normal indoor humidity levels. So therefore what that does is that means that you don't get the mould growth and you don't get damage to your windows, they don't start rotting away or anything, paint finishes aren't damaged, you just end up with a higher quality home as a result. So that's for passive house standards of retrofit. And then within the UK, the ACB, of which I'm now a trustee. Starting from this year, 2014, the ACB Carbon Light has got a silver standard, which is less onerous, should we say, than Passivhaus insofar as at a numerical level. We're looking for 40 kilowatt hours per metre square per annum rather than 15. But what you find is that the same quality assurance measures underpin the design process. So therefore we've got PHPP, Passive House Planning Package, we look at thermal bridging, we're designing for high standards of air tightness, we might have ventilation systems which have got to be thought about carefully, we've got to have the right data to use in that context, and we've got to make sure everything's commissioned properly. And then ideally we also then go and we monitor the performance of the building after it's been built, and that's something that I try to instill into my practice on every project, so that we measure temperatures, humidities, and we also measure the energy use and the likes. So I hope this has set a context not only for Passivhaus but also for the fact that you can use Passivhaus can be used on the retrofitting homes, and also that there's ACB Silver, which uses the same quality assurance methods but doesn't set the same numerical target. It's a little bit more relaxed, so therefore you can get a high quality building which is slightly more, might be a little bit more cost effective in your context. And the other benefit is that if you just near miss a Passivhaus, then you know that you can still get a certificate for that performance if that's what you're seeking. One thing to mention is that Passivhaus buildings don't have to be certified to be declared as being a Passivhaus, though it does require that you obviously have satisfied all of the core criteria. So you've got to make sure that people really understand that, and the best way to do that is to make sure that they've built Passivhauses before. So if they've built 25 or more Passivhauses, then statistically you can be pretty confident that they know what's going on, they know how to do it, because they've delivered this stuff repeatedly, time and time again. Okay, so thanks for watching this short training video, and if you'd like to get any more information, if you'd like to get onto my newsletter, then please sign up down below with your name and email address, and I'll keep you updated as things go on. Okay, well, thank you very much, and keep in touch.